Okay, so we are going to look at day 6, January 20th, chapter 18, modeling the distribution of sample proportions. So a distribution, again, is just a group of numbers. Sample proportion, a proportion is p or p hat, and we'll talk about those down here. A proportion is like a probability, a decimal, a fraction. So one of the major tasks of a statistician is to discover the proportion of individuals in a population who possess a certain property or characteristic. So, for example, P could be the proportion of all U.S. residents who are unemployed. The way we might gather that information, we probably couldn't unless we did a census, okay? P is the proportion of all East High students with at least one AP class. This would be easier to get the information. So, again, unfortunately, without conducting a census, we'll never know the true value of P. P is the proportion of people who have that given characteristic. It's like the probability of success. P is the same thing it was in the binomial distribution, the probability of success, the probability someone has a characteristic. Okay, the true proportion, or sorry, the population proportion, or true proportion, so we'll never, well, sometimes we can get it. Every 10 years we can do a census, but so until then we can't. And there's a lot of things questions we ask that we just don't ask in the census. So instead, statisticians will estimate P by taking a sample and computing the sample proportion, P hat. So P is the variable we use for the population proportion, the true value. Usually we think of this as the unknown, although, you know, we have values from censuses that we use to compare it to. We want this, we are going to use this, P hat, which is the sample proportion. Okay, sample proportion is P hat right here. So P hat is the number of successes in the sample, which is X, divided by N, the sample size. N is always the sample size. X is the number of successes. So, no, since X is the number of successes, it is a binomial random variable. So all we're doing for a sample proportion is taking a binomial and dividing it by N. So now we're going to see what the distribution of P hat looks like and then develop formulas on the next page. So suppose that 22% of registered voters in Arizona are senior citizens. That is, they tell us that the true proportion is 0.22. If we were to take a sample of size 100 and find the sample proportion of senior citizens P hat, so N equals 100, find P hat, what are the values we might get? Well, the values you might get, if the true value is 22% and every one of us goes out and collects a sample of size 100, we're going to find, you know, maybe the sample proportion is 0.21 or 0.20 or 0.23 or 0.24 or 0.19 or 0.25 or 0.17, okay? How far away could we go? Well, we would expect most of the samples to be fairly close to this. Occasionally you'll get a sample that's like 0.12 or 0.32. Okay, so these could happen, but not as often as these, if you know that this is true. Okay, so what we're doing a lot of times here is, you know, we know a value, but we're trying to see if maybe it's still the same or estimate that value through a sample. So now we want to look at what the distribution of P hat looks like. I want you to realize that the distribution of P hat here is the same as the distribution of a sample proportion. Sample proportion is P hat. So P hat is the variable we use to represent a sample proportion. So we start with what we know, and what we know is that we have X. And X is the number of senior citizens in my sample. Okay, and N is 100, and we'll use that in a little bit. So X is right now binomial. Okay, X is binomial, and N comma P is the way we write a binomial. So X is binomial, a 100 comma 0.22. So now we need to check because we're going to, we want to model the distribution of P hat. Okay, well, we don't know much about P hat right now, but what I do know is that I could change this into a normal distribution. Okay, so a normal distribution I would have to check to see that n times p is greater than or equal to 10, and n times q is greater than or equal to 10. That's just to see if the normal model is appropriate. So n times 0.22, that's 22, that's greater than or equal to 10. And 100 times 0.78, which is q, is 78, so both are greater than or equal to 10, so normal is okay. All right, so we're getting to the distribution of p hat. First, we're going to do the normal. So now we know that we can change this into a normal, but actually, p hat is what we're really looking for. So we have to think about what are we doing? Well, let's first of all change binomial to a normal. So to change the binomial to a normal, binomial to a normal, and then we're going to change that into a p hat. Okay, so binomial, x is binomial, n comma p. Change it to a normal, x is normal, n times p, comma, square root of n times p times q. Okay, now we need to look at how do we change that to p hat. Well, what did I do to find p hat? Well, go up and look at the formula for p hat. P hat is the number of successes in the sample divided by n. Okay, so if I take a sample of size 100, okay, size 100, and I get 78 successes or 25 successes, then I would write it as 25 over 100. Okay, so let's first change it to a normal, and then we'll look from here to here. So we have x is binomial, 100, comma, 0.22, and normal then would be x is normal. Well, n times p is 22. That's actually the number of successes out of 100. That's the number of successes. And then the square root of n times p times q is 4.14. Okay, so this is binomial, this is normal. Now let's check it to p hat. All we do to get p hat is divide by n. All we do to get p hat now is divide by n. So x is, now, we still say normal. This is basically, we still say normal. And n times p divided by p. So now we take n times p divided by, n, divided by n, and the square root of n times p times q divided by n. So we actually already have n times p and n times q, so if we just divide that by 100, so 22 divided by 100, so 22 divided by 100, and 4.14 divided by 100, so the p hat, and so we'll switch this, p hat is approximately normal. This should all be p hats. P hat is approximately normal, and the mean is 0.22, and the standard deviation is 0.04. And so you could draw a picture of this, 0.22, 0.26, 0.30, 0.34, and then 0.18, 0.14, 0.10. And that would be my distribution of p hat. Alright, so now the next page we just formally, officially define this. I actually developed the formulas that are on the next page here, but there's also explanation at the bottom. So these are the general properties of the sampling distribution of the sample proportion. We're going to let p hat be the proportion of successes in a random sample of size n from a population whose proportion of success is p. Okay, so a lot of times we'll know p, okay, we'll know this, and we will want to, and p hat is the proportion of successes in a sample. Okay, this is the true population value, p is, and p hat is the sample proportion. Okay, gotta get that straight in your head. So, denote the mean value of p hat by the mean of p hat, and the standard deviation of p hat by sigma p hat. Then the mean of p hat is just p, whatever the true proportion is, and the standard deviation of p hat is the square root of pq over n. And this actually, the proof of both of these is down here at the bottom, and we actually really did these when we just did the last problem. So if you just look real fast, how do I get that the mean of p hat is just p? This is formally defining the distribution of p hat, okay? The sampling distribution of the sample proportion. So how did I get p, the mean of p hat is p? Well, the mean of x we had on the other side, that was n times p, and we just divided it by n. So to get p hat from a binomial, we just divided by n. So that's all we did. The n's actually cancel, and you get p in general. With the standard deviation, we took the standard deviation of the x, the binomial, changed to normal, and we just divided by n. And so that was the square root of npq divided by n. Well, if you do a little algebra here, and you say, well, basically, if I put this, I need a square root on the top and the bottom in order to cancel. Because I notice there's an n on the top and bottom. So the n I have to write as the square root of n squared. Well, then you can put, if there's a square root on the top and a square root on the bottom, you can put it over the whole thing. And then the one n cancels and you get this. So these are the formulas you need to memorize for the sampling distribution of the sample proportion. Okay? And then it says when n is large and p is not too close to 1 or 0, the sampling distribution of p hat is approximately normal. So basically it says when n is large, okay, so you've asked enough people, and p is not too close to 0 or 1, it's closer to 0.5, then it's approximately normal. Now, when we changed binomial into normal, we had to check conditions. So we have conditions we have to check. Before we can use the sampling proportion of the sampling distribution of the sample proportion, we need to check all of these conditions every single time. And these are important. I'm going to give each of them names, and you need to memorize these and use them every time. So, and then the next video goes through this example. So conditions for these property conditions. For all of these things to hold up here, you have to check the following. The data is from a random sample from the population of interest. Okay, this is called the randomization. Randomization, okay? Randomization condition. Was it from a random sample? They either stated in the problem. If they stated in the problem, you say stated in the problem, or they don't, and then you say I will assume that it's from a random population of interest, okay? And you should say from the population of interest. In fact, you should state it in the context of the problem. So like down here, in this problem, we're talking about registered voters in Arizona who are Democrats. So we would say, well, just registered voters in Arizona would be, we would assume that this is a random sample from registered voters in Arizona. Okay, B, the sample size is less than 10% of the population. Okay, this is called the independence condition. Independence condition. Okay, we had this one before. Okay, every time you ask someone from a population, you're reducing the number of people in the population. And so what you need to do is you have to make sure you don't sample too many so it's still considered independent. So you would say something like 50 down here, we're going to ask 50 people. We would assume that 50 is less than 10% of all registered voters in Arizona. Okay, so the trials are independent. Okay, the trials are independent since we're sampling less than 10% of people. And then finally the large sample size condition. So we've got the randomization, the independence, and the large sample size. And the large sample size is the same one we did before. N times P is greater than or equal to 10, and N times Q is greater than or equal to 10. So those are the three conditions you must check every single time before you go on and change to use a normal distribution. So the next video goes over this problem right here, this example, and the rest of the notes. So thank you very much.